Hello and welcome. Tonight we're going to explore one of the universe's most mysterious phenomena, black holes. These cosmic enigmas sit at the edge of what we can understand, where the familiar rules of reality bend and sometimes break entirely. If you enjoyed this journey through the darkness, consider subscribing to the channel for more peaceful explorations of science. Now let's begin. Let's start with what a black hole actually is, because the name itself can be misleading. A black hole is a region of space-time, not just space, but the fabric that weaves space and time together, where gravity has become so extraordinarily strong that nothing, not even light itself, can escape once it crosses a particular boundary. That boundary has a name, the event horizon. It's a point of no return, written into the geometry of the universe itself. What makes this remarkable is that we're not talking about some exotic form of matter or a different set of physical laws. Black holes follow the same rules as everything else in the cosmos. It's just that under certain extreme conditions, those rules lead to something so strange that it challenges our everyday intuition. Einstein's equations of general relativity predict that when enough mass gets compressed into a small enough space, it warps space-time so severely that it creates this trap from which there's no escape. And here's what makes it even more fascinating. This is one of the few places in the universe where those beautiful equations actually predict their own breakdown, where they point towards something they can't fully describe. In a sense, black holes are nature's way of showing us the limits of our current understanding, the quiet signposts at the edge of the map saying, "Here be dragons." For now, just let that sink in. These objects exist not in spite of physics, but because of it. Despite their name, black holes aren't actually holes at all. That might seem obvious once you think about it, but the name has a way of creating a certain image in our minds, a tunnel, an opening, an absence. In reality, black holes are among the most substantial objects in the entire universe. They're not empty. They're not gaps in space. They're incredibly dense concentrations of matter, massive beyond our usual capacity to imagine. Think of it this way. Imagine taking all the mass of a star many times larger than our Sun and compressing it down smaller and smaller until all of that matter occupies a space far tinier than the star it came from. In some cases, according to our current theories, all of that mass might be compressed into a single point, something called a singularity. Now, whether singularities truly exist as mathematical points of infinite density, or whether they're placeholders for physics we don't yet understand, remains an open question. But what we do know is this: the mass is there, real and present, warping everything around it. Black holes are perhaps the most concentrated form of there-ness that exists. They're the opposite of nothing. And yet, because their gravity prevents even light from escaping, they appear to us as voids, as absences. It's a beautiful paradox. The most massive objects appear as darkness, defined not by what they are, but by what they prevent us from seeing. Maybe that's fitting. Maybe the densest truths are sometimes the hardest to illuminate. The idea of black holes is older than you might think. Long before Einstein revolutionized our understanding of gravity, before we knew about relativity or the curvature of space-time, a British natural philosopher named John Michell imagined something remarkably similar. The year was 1783, and Michell was working within the framework of Newtonian physics, the same physics that explained falling apples and planetary orbits. Michell asked himself a question. What if a star were so massive and so dense that the escape velocity from its surface exceeded the speed of light. In Newtonian terms, escape velocity is the speed you'd need to break free from a gravitational pull. For Earth, it's about 11 kilometers per second. For a more massive object, it's higher. Michel calculated that if a star were massive enough, that escape velocity could theoretically reach the speed of light itself, and if that happened, he reasoned, light wouldn't be able to escape. The star would be invisible. He called them dark stars. What's extraordinary is that Michel arrived at this conclusion using a theory of gravity that we now know is incomplete, a framework that doesn't account for the strange relationship between space, time, and gravity that Einstein would later reveal, and yet, through careful reasoning and mathematics, he glimpsed something true about the universe. He couldn't have known about event horizons or space-time curvature, but he sensed that gravity, taken to its extreme, might create invisible objects. Sometimes the right question, asked with curiosity and rigor, can lead you toward truths that won't be fully understood for centuries. Michel's dark stars waited patiently in the mathematics, sleeping in equations, until the universe was ready to reveal them more fully. Fast forward to 1916. The world is in the midst of the Great War, and a German physicist named Karl Schwarzschild is serving on the Eastern Front. It's hard to imagine a setting less conducive to profound theoretical work. Trenches, artillery, the chaos of war. And yet Schwarzschild receives a copy of Einstein's recently published General Theory of Relativity, and something ignites in his mind. Einstein's equations were notoriously difficult. They described how mass and energy curve space-time, creating what we experience as gravity. But they were so complex that even Einstein himself had only found approximate solutions for specific situations. Schwarzschild decided to look for an exact solution, the precise description of space-time around a perfectly spherical, non-rotating mass. And remarkably, incredibly, he found it. While stationed in the trenches, amid the machinery of destruction, Schwarzschild solved Einstein's field equations exactly, describing what space-time looks like around a massive object. What he discovered, encoded in those equations, was the mathematical description of what we now call a black hole. He found that there was a critical radius, now called the Schwarzschild radius, where something peculiar happens. For any given mass, if you compress it within that radius, you create an event horizon. Schwarzschild sent his solution to Einstein, who was astonished. He presented it to the Prussian Academy of Sciences in 1916. Tragically, Lord Schwarzschild died just a few months later from an illness contracted during the war. He never saw how central his solution would become to our understanding of the universe. But in these stolen moments between battles, working by lamplight perhaps, he glimpsed the architecture of space-time around its most extreme structures. Sometimes the most profound insights emerge in the least likely circumstances, as if the universe insists on being understood regardless of the setting. For decades after Schwarzschild's discovery, physicists struggled with what to call these objects. The names they used reflected their uncertainty and discomfort. Some called them gravitationally collapsed objects, accurate but unwieldy. Others used terms like frozen stars, which captured something true about how they appear from the outside. Because of time dilation, an observer watching something fall toward the event horizon would see it appear to slow down and freeze, never quite crossing that boundary, as if time itself had stopped. The object would also appear to redden, its light stretched by gravity until it faded into darkness. So Frozen Star had a certain poetic accuracy to it. But in 1967, the physicist John Archibald Wheeler was giving a lecture, and he needed a catchier term. According to Wheeler's own account, he didn't invent the phrase black hole out of thin air. He'd heard it used in other contexts, possibly even referring to the infamous prison cells in Calcutta. But he recognized that it captured the essential nature of these objects, regions of space-time that absorb everything and emit nothing, at least in the classical sense. The name stuck instantly, and it had a certain drama to it, a simplicity that the more technical terms lacked. Wheeler later expressed some ambivalence about the name, wondering if it was too colloquial, too informal for such a fundamental phenomenon. But perhaps its very accessibility is what made it so powerful. Black hole sounds like something from science fiction, and yet it describes something utterly real, something woven into the fabric of reality by the same mathematics that governs falling leaves and orbiting planets. The name invites both scientists and poets, and maybe that's exactly what these objects deserve. A name that acknowledges they sit at the intersection of the precisely calculable and the deeply mysterious. Sometimes the simplest names carry the most weight. Black holes come in different sizes, and understanding this helps us see them not as a single phenomenon, but as a family of related objects, each with its own origin story. Astronomers generally categorize them into three main types, though the boundaries between them are still being explored and debated. First, there are stellar mass black holes. These are the smallest of the family, though small is relative. They typically contain anywhere from a few times the mass of our Sun to perhaps 100 times that mass. They're born from the deaths of massive stars, which we'll explore more deeply in a moment. Then there are supermassive black holes, the giants that lurk at the centres of galaxies. These monsters contain millions or even billions of times the Sun's mass. The one at the heart of our own Milky Way weighs in at about 4 million solar masses, while others dwarf even that. And then, occupying a puzzling middle ground, are intermediate mass black holes, hundreds to thousands of solar masses. These are the most mysterious of the three types, because we're not entirely sure how they form. We found hints of their existence, shadows in the data, but they remain elusive. What's fascinating is that each type seems to form through different cosmic processes, suggesting that there are multiple pathways to creating these extreme objects. The universe, it seems, has found several different ways to compress matter beyond the point of no return. It's a bit like discovering that there are multiple recipes for the same fundamental dish, each starting from different ingredients but arriving at the same essential result. And the fact that we've categorized them into three types doesn't mean the universe necessarily thinks of them that way. Perhaps there's a continuous spectrum, with black holes of every possible mass, and we've simply found it convenient to draw lines between them. The cosmos rarely respects our neat categories. It tends to blur the boundaries we try to draw, reminding us that our classifications are tools for understanding, not fundamental truths about how reality organizes itself. Let's talk about the event horizon, because it's one of the most conceptually slippery aspects of black holes. When you first hear the term, you might picture it as a kind of surface, like the skin of a bubble or the boundary of a soap film. But it's not a physical thing at all. There's nothing there to touch, no material marking the boundary. Instead, the event horizon is a mathematical surface, a point of no return written into the geometry of space-time itself. Here's what makes it so strange. The event horizon is defined by what happens to light. Specifically, it's the boundary beyond which light, travelling outward, can no longer escape. It's trapped by gravity and pulled inexorably inward. And since nothing can travel faster than light, anything else that crosses that boundary is trapped as well. But from the perspective of someone crossing the event horizon, there's nothing special about that moment. You wouldn't feel anything unusual. There's no wall, no barrier, no sudden change. If you were falling toward a supermassive black hole, one with a gentler gravitational gradient near its event horizon, you might not even notice the instant you crossed it. You'd just keep falling and accelerating toward the center. The event horizon is less like a fence and more like a point in a river where the current becomes stronger than any swimmer could overcome. Before that point, you could theoretically swim back upstream. After it, you're going with the flow whether you want to or not. But the water itself doesn't change at that precise point. The transition is smooth, continuous. In the case of a black hole, that current is the warping of space-time itself. The event horizon marks the place where every possible future path, every trajectory through space-time, leads inward. It's a boundary in possibility space, not in physical space. And that's what makes it so deeply strange. You can cross a line you can't see, a boundary with no substance, and suddenly find that all possible futures lead to the same place. Or perhaps it's fitting that the most dramatic boundary in the universe is completely invisible and intangible, defined not by what it is, but by what it forbids. At the very center of a black hole, according to our current theories, lies something called a singularity. And if the event horizon is conceptually slippery, the singularity is where our understanding slides off the map entirely. Mathematically, it's described as a point of infinite density, all the mass of the black hole compressed into a space with zero volume. It's where space-time curvature becomes infinite, where the equations that describe gravity produce infinities in their solutions. Now, physicists generally don't trust infinities when they appear in their equations. An infinity usually signals that the theory is being pushed beyond its limits, if into a regime where it breaks down and needs to be replaced by something deeper, and that's almost certainly what's happening at the singularity. General relativity, Einstein's beautiful theory of gravity and space-time, works magnificently almost everywhere in the universe. But it's a classical theory, meaning it doesn't account for quantum mechanics, the physics of the very small. And inside a black hole, at the singularity, the very small and the very massive collide. You have all the mass of the black hole in a region where quantum effects should matter enormously. We don't yet have a complete theory of quantum gravity, a framework that successfully merges general relativity and quantum mechanics. String theory, loop quantum gravity, and other approaches are all attempts to build that theory, but none of them are complete or fully verified. So when our equations tell us there's a singularity at the center of a black hole, what they're really telling us is, something happens here that I can't describe. You need a better theory. It's humbling in a way. We can send equations down toward the center of a black hole, following the mathematics as far as it will go, and it eventually throws up its hands and says, "Beyond here I don't know." The singularity represents the edge of our current knowledge, a place where new physics must emerge, and maybe that's okay. Maybe it's even beautiful, these cosmic objects that contain, at their very hearts, an admission that we have more to learn. How does a black hole actually form? For stellar mass black holes, The answer lies in the death of massive stars. These stars spend most of their lives in a delicate balance. Gravity is always pulling inward, trying to compress all that stellar material into the smallest possible space. But the nuclear fusion happening in the star's core creates outward pressure, pushing back against gravity's relentless pull. As long as the star has fuel to burn, this equilibrium holds. The star shines steadily, converting hydrogen into helium, helium into heavier elements, year after year, sometimes for billions of years. But eventually every star runs out of fuel. For stars at least 20 times more massive than our Sun, what happens next is catastrophic. When the core finally exhausts its nuclear fuel, there's nothing left to hold up the star against its own gravity. The core collapses in a fraction of a second. Imagine a region larger than Earth, compressed into a space the size of a city, then smaller, all in less time than it takes to blink. The collapse is so sudden and violent that it triggers a supernova explosion. The outer layers of the star are blown into space in a blast so bright it can briefly outshine an entire galaxy. But the core keeps collapsing. For the most massive stars, not even the quantum pressure that holds up neutron stars can stop the collapse. The core just keeps compressing, past any known form of resistance, until it forms a black hole. In a matter of seconds, a star that shone for millions of years becomes a dark wound in space-time. And what's remarkable is that this isn't some rare cosmic accident. It's a natural endpoint for massive stars written into their life cycle from the beginning. The very processes that make stars shine also ensure that the most massive among them will eventually collapse into darkness. There's something almost poetic about it. Stars are engines of light, but some of them are destined to become sources of absolute darkness. The universe contains its own contradictions, and they're built into the life cycle of its most spectacular objects. Not every massive star becomes a black hole, though, and that's an important detail. Stars between about 8 and 20 times the mass of our Sun also exhaust their fuel and undergo core collapse, but something different happens. Instead of compressing all the way down to a black hole, the core stabilizes as something called a neutron star. These are objects so dense that a teaspoon of their material would weigh about as much as a mountain on Earth. They're held up by a quantum mechanical effect called neutron degeneracy pressure. Essentially, neutrons packed so tightly that quantum rules prevent them from being compressed further. So there's a boundary, somewhere around 20 solar masses, above which core collapse creates a black hole, and below which it creates a neutron star. But the exact location of that boundary is surprisingly fuzzy. It depends on subtle factors: the composition of the star, how fast it's rotating, what happens during the supernova explosion itself. Small differences in these factors can determine whether a dying star's core becomes a neutron star or tips over that edge into becoming a black hole. What this means is that there's a cosmic threshold, a kind of tipping point, where gravity's victory becomes absolute. On one side of that line, quantum mechanics holds the line, creating an object of almost incomprehensible density, but still something describable with known physics. On the other side, gravity wins completely, compressing matter beyond any quantum resistance, creating a black hole. And the fact that we can't predict exactly where that line falls, that it depends on the particular circumstances of each stellar death, makes it even more fascinating. The universe operates on these thresholds, these delicate balances. Sometimes the difference between one outcome and another, between a neutron star and a black hole, comes down to details we're still trying to understand. In those details, in that narrow, uncertain space between one fate and another, lie some of the most interesting physics in the cosmos. Now let's turn our attention to supermassive black holes, because they present a different kind of mystery. These cosmic giants sit at the centers of most galaxies, including our own Milky Way. And when we say supermassive, we're talking about objects that contain millions or billions of times the mass of our Sun. The one at the heart of our galaxy, Sagittarius A star, weighs in at about 4 million solar masses. Others are far larger. Some exceed billions of solar masses, objects so massive that their event horizons could swallow our entire solar system with room to spare. Here's the puzzle. We don't fully understand how these monsters formed. If they grew simply by consuming matter from their surroundings, gas, dust, unlucky stars, or by merging with other black holes, the math doesn't quite work out. The universe is only about 13.8 billion years old. That sounds like plenty of time. Yeah, but when you calculate how fast a black hole can actually grow through accretion, you run into a problem. There's a limit to how quickly a black hole can consume matter, set by the pressure of radiation from the superheated material falling in. This is called the Eddington limit. If you start with a stellar mass black hole, say 100 times the mass of the Sun, and let it feed at the Eddington limit for the entire age of the universe, it still couldn't grow into a billion solar mass behemoth we observe. And yet we see supermassive black holes that existed when the universe was less than a billion years old, when there was even less time for them to grow. So something else must have happened. Either these black holes were born big, seeded by some process we don't yet understand, or they grew faster than the Eddington limit suggests they should have, perhaps through super Eddington accretion during brief periods, or through frequent mergers, or through some combination of factors we're still piecing together. It's one of those wonderful scientific mysteries where we have plenty of data. We know these objects exist, we can measure their masses, but the story of their origin remains tantalizingly incomplete. The universe managed to build these giants quickly, within the first billion years of cosmic history, and we're still working backward trying to figure out how it pulled off that trick. Sometimes knowing that something exists is just the beginning of the puzzle. One possibility for how supermassive black holes formed so quickly involves skipping the star stage entirely. Imagine the early universe. Less than 1 billion years after the Big Bang. Galaxies are just beginning to form, and there are massive clouds of primordial gas, mostly hydrogen and helium, that haven't yet collapsed into stars. Under the right conditions, some of these clouds might have been so massive and so perfectly positioned that they collapse directly into black holes without ever forming stars first. These hypothetical objects are called direct collapse black holes, and they would have been born already containing tens of thousands or even hundreds of thousands of solar masses. That's a much better starting point if you're trying to grow to 1 billion solar masses within the limited time available in the early universe. Think of it as giving the black hole a head start. Instead of beginning as a stellar remnant and having to gradually accumulate mass, it starts already massive and just needs to grow from there. But direct collapse is a delicate process. The conditions have to be just right. The gas cloud needs to be massive enough, and it needs to collapse without fragmenting into smaller clumps that would form stars instead. This probably required a specific environment, perhaps a region bathed in ultraviolet radiation from nearby young galaxies, which would heat the gas just enough to prevent it from fragmenting, but not enough to blow it apart. It's a Goldilocks scenario. Not too hot, not too cool, but just right for a catastrophic direct collapse into a black hole. We haven't directly observed this process happening. It would have occurred in the very distant past, and seeing it would require observing extremely faint objects in the early universe. But it remains one of the leading theories for how supermassive black holes got their start. There's something almost elegant about it. The universe finding a shortcut, a way to build massive black holes without going through the usual stellar life cycle. And it reminds us that the cosmos has multiple pathways to the same destination, that nature isn't limited to just one method for creating its wonders. Perhaps in the early universe, when conditions were different and possibilities were wider, direct collapse was commonplace. Perhaps those first black holes seeded the centres of the first galaxies, and everything that came after, all the structure we see in the universe today, grew up around them. Once a black hole exists, regardless of how it formed, it can continue to grow. There are two main ways this happens: accretion and merger. Accretion is the process of pulling in matter from the surroundings. If a black hole sits in a region with gas and dust nearby, that material can spiral inward, forming what's called an accretion disk. As the material falls closer to the event horizon, it heats up, sometimes to millions of degrees, and radiates enormous amounts of energy before finally crossing the point of no return. This is a relatively slow process, limited by how much material is available and by the physics of how fast a black hole can actually consume matter without blowing that matter away with radiation pressure. Mergers are different. They're dramatic, violent events where two black holes, perhaps orbiting each other for millions of years, finally spiral together and coalesce into a single larger black hole. When this happens, it releases a tremendous amount of energy in the form of gravitational waves, ripples in space-time itself that propagate outward at the speed of the light. We've been detecting these mergers since 2015, listening to the universe's most violent events with our gravitational wave observatories. What's fascinating is that each of these growth mechanisms writes a kind of history into the black hole. A black hole that grew primarily through steady accretion might have a different spin or mass than one that grew through a series of chaotic mergers. And by studying the black holes we observe today, their masses, their spins, their positions, we can begin to reconstruct their biographies, piecing together how they grew over cosmic time. Some black holes have had relatively quiet lives, slowly accumulating mass from their surroundings. Others have been through multiple mergers, cosmic collisions that fundamentally changed them. Each black hole carries its history encoded in its properties, though reading that history requires careful observation and sophisticated modelling. In a sense, every black hole is like a fossil, preserving information about the conditions in which it formed and grew. And just as paleontologists can look at a fossil and infer things about ancient environments, astronomers can look at a black hole's properties and infer things about cosmic history. The universe keeps records, even if those records are sometimes written in the curvature of space-time or the spin of a horizon. We just have to learn how to read them. Let's linger for a moment on those mergers, because they're among the most spectacular events in the universe. When two black holes orbit each other, they're essentially dancing through space-time, their immense masses creating waves in the fabric of space itself. At first, when they're far apart, these gravitational waves carry away only a tiny amount of energy. The black holes orbit each other for perhaps millions or billions of years, their dance imperceptibly slow from a human perspective. But as gravitational waves carry energy away from the system, the orbit gradually shrinks. The black holes spiral closer together, orbiting faster and faster. Eventually, in the final moments before they merge, they're whipping around each other multiple times per second, their event horizons distorted by the tremendous gravitational forces, space-time churning in ways that are difficult to visualize. And then they collide. They merge into a single, larger black hole, and in that instant, they release more energy in gravitational waves than all the stars in the observable universe are emitting in light at that same moment. Think about that for a second. More energy than all the stars, not as light, but as ripples in space-time itself. Those waves spread outward in all directions, travelling at the speed of light, crossing millions or billions of light years of space. And when they finally reach Earth, passing through our planet and our bodies, they stretch and squeeze space-time by an amount smaller than the width of a proton. That's why it took us so long to detect them. We had to build instruments exquisitely sensitive enough to measure distortions in space-time 1,000 times smaller than an atomic nucleus. But we did it. In 2015, and the LIGO detectors caught the gravitational waves from a black hole merger that happened over 1 billion light-years away. For the first time, humanity heard the sound of space-time ringing like a bell, the aftershock of a cosmic collision, and since then, we've detected dozens more. The universe, it turns out, is alive with these events. Black holes are merging all the time, across vast distances, and now we can listen to them. Each merger tells us something about the masses of the black holes involved, how they were spinning, even something about the properties of space-time itself. We've opened a new sense, in a way. For all of human history, we could only see the universe. Now we can feel it vibrating. Here's something that seems almost contradictory. Black holes, despite being objects from which nothing can escape, what might actually evaporate. This idea comes from Stephen Hawking, who in 1974 proposed something now called Hawking radiation. It's a quantum mechanical effect that occurs right at the event horizon, where the extreme curvature of space-time meets the strangeness of quantum physics. In the quantum world, empty space isn't really empty. It's filled with what are called virtual particles, pairs of particles and antiparticles that pop into existence for the briefest instant and then annihilate each other. Normally this happens so quickly that it doesn't violate any laws of physics. It's just part of the quantum foam that underlies reality. But near the event horizon of a black hole, something different can happen. If a particle-antiparticle pair appears right at the horizon, one particle might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole emitted a particle, and because energy is conserved, the black hole must have lost a tiny bit of mass to account for that escaped particle. This process is incredibly slow for large black holes. A supermassive black hole would take vastly longer than the current age of the universe to evaporate through Hawking radiation. We're talking timescales of 10 to the power of 100 years or more, a 1 followed by 100 zeros. But here's the interesting part. As a black hole evaporates and gets smaller, it gets hotter and radiates faster. So the process accelerates. The final stages of a black hole's evaporation would happen quickly in a burst of radiation. A black hole the mass of a mountain would evaporate in about the age of the universe. Anything smaller would go even faster. We've never observed Hawking radiation. It's far too faint to detect from any real black hole. But if it's real, and most physicists believe it is, it means that black holes aren't truly eternal. Given enough time, unimaginable amounts of time but still finite, even the largest black holes will evaporate away, leaving behind only radiation and perhaps some mysteries about what happened to all the information that fell in. It's a reminder that permanent in physics often just means lasts a very long time. Even the darkest objects eventually return their energy to the universe. Perhaps that's comforting in a cosmic sense. Nothing lasts forever, not even the things that seem most unchangeable. Time near a black hole behaves in ways that challenge our everyday understanding, and nowhere is this more apparent than near the event horizon. According to general relativity, gravity doesn't just bend space, it also bends time. The stronger the gravitational field, the slower time flows relative to someone in a weaker field. This effect is called gravitational time dilation, and near a black hole it becomes extreme. Imagine you're watching a friend fall toward a black hole while you stay at a safe distance. As your friend gets closer to the event horizon, something strange happens. They appear to slow down. Their movements become more and more sluggish, as if they're moving through increasingly thick syrup. If they wave to you, that wave takes longer and longer to complete. And as they approach the event horizon itself, they seem to freeze entirely. From your perspective, they never quite cross it. They become stuck at that boundary, frozen in time, just their image growing dimmer and redder as the light they emit gets stretched and weakened by gravity. But here's what makes this truly mind-bending. From your friend's perspective, nothing unusual happens at all. They don't feel themselves slowing down. They don't notice anything special about the moment they cross the event horizon, at least not if the black hole is large enough. They just keep falling, accelerating smoothly toward the center. They cross the horizon in a finite amount of their own time. To them, time flows normally. It's only when you compare their clock to yours that the difference becomes apparent. This creates a strange asymmetry in the universe. Two observers, both following valid paths through space-time, experience the same event completely differently. One sees someone frozen at the edge of a black hole for eternity. The other experiences a smooth, finite journey past the horizon, and both perspectives are correct. Neither is more true than the other. They're just different slices through the same four-dimensional space-time. Maybe that's one of the deepest lessons black holes teach us, that time isn't a single, universal river that flows the same for everyone. It's flexible, personal, dependent on where you are and how you're moving. The universe contains multiple timelines, all real, all valid, all just different ways of experiencing the same underlying reality. Let's stay with that falling observer for a moment, because their experience reveals something profound about the nature of the event horizon. From the outside, as we just discussed, the event horizon seems like a dramatic boundary, the place where time freezes, where things get stuck forever. But from the inside, from the perspective of someone crossing it, the event horizon is completely smooth and unremarkable. If you are falling into a sufficiently large black hole, a supermassive one, where the tidal forces near the horizon are relatively gentle, you wouldn't see any kind of barrier as you approached. There's no wall, no surface, no sign warning you that you're about to cross the point of no return. Space doesn't look distorted or weird right at the horizon. You just keep falling, surrounded by the same darkness you saw a moment before. The only clue that something significant had happened might be looking back up at the universe you left behind. You'd see things happening faster and faster, time-lapse style, as the gravitational time dilation worked in reverse for light coming from the outside universe. But the horizon itself? Perfectly smooth. This is sometimes called the principle of equivalence, and it's one of the cornerstones of general relativity. The idea is that if you're in free fall, not feeling any forces acting on you, the laws of physics should look the same everywhere, even at an event horizon. There's no locally detectable difference between one region of space-time and another if you're falling freely through both. The event horizon is a global property, something that becomes apparent only when you consider the entire structure of space-time, not a local feature that you could detect by doing experiments in your immediate vicinity. It's almost like a cosmic one-way door that you can walk through without noticing. You only realize what you've done afterward, when you try to turn around and discover that every direction you can go leads further inward. By the time you notice, it's already too late. There's something almost quietly terrifying about that. The most consequential threshold in the universe is one you can cross without knowing. But there's also something beautiful about it. The universe doesn't need dramatic markers or warning signs. The mathematics alone creates boundaries, and those boundaries are written so deeply into the structure of space-time that they don't need to announce themselves. They just are. Not all black holes are static, eternal voids. Many of them spin, and when a black hole spins, things get even stranger. The rotation doesn't just affect the black hole itself. It actually drags space-time around with it. Yeah, like a spinning ball in honey would drag the honey along. This effect is called frame dragging, or the Lense-Thirring effect, and near a rotating black hole it becomes extreme. The region where this happens most dramatically is called the ergosphere. It sits just outside the event horizon, and it's a place where space-time itself is being pulled around the black hole so forcefully that nothing can remain stationary. Even light can't stand still. If you were in the ergosphere, even if you fired your rockets at full power trying to hover in one place, you'd still be dragged around the black hole in the direction of its rotation. It's not that you're being pulled toward the black hole necessarily. You could still escape from the ergosphere, unlike from inside the event horizon, but you can't not rotate with it. The very frame of reference you exist in is being swept along. Some black holes spin incredibly fast, close to the theoretical maximum, which is the speed of light at the event horizon. For these rapidly rotating black holes, the ergosphere can extend quite far out from the event horizon. And this creates some fascinating possibilities. There's a process, proposed by Roger Penrose, where you could actually extract energy from a rotating black hole by dropping something into the ergosphere at just the right angle. Part of it falls into the black hole, but another part escapes, and under the right conditions, the escaping part carries away more energy than you put in. The extra energy comes from the rotational energy of the black hole itself. You're essentially slowing down the black hole's spin and converting that into usable energy. This is still entirely theoretical. No one has tried to extract energy from a black hole's rotation, and we probably won't for a very long time, if ever. But the fact that it's possible in principle says something profound. Even black holes, the darkest objects in the universe, aren't just passive absorbers. They can be active participants in cosmic processes, stores of rotational energy that could, under the right circumstances, power unimaginable engines. The universe contains not just matter and energy, but information about motion and spin, and that information is stored in the rotation of space-time itself. Let's explore that Penrose process a bit more, because it opens up some fascinating speculations about the far future. Imagine an advanced civilization, millions or billions of years from now, that has exhausted more conventional energy sources. They could, in principle, use a rotating black hole as a power source. By carefully dropping material into the ergosphere and collecting what escapes, they could extract the rotational energy stored in the black hole's spin. There's even a more sophisticated version of this idea called the Blandford-Zerniak process, which wouldn't require physically dropping objects in. Instead, it would use magnetic fields threading through the ergosphere to extract energy. This might not be just theoretical. We think this process actually happens naturally around some black holes, powering the enormous jets of particles and radiation that we observe shooting out from certain active galactic nuclei. The black hole isn't creating the energy out of nothing. It's converting its spin energy into the kinetic energy of those jets. For a sufficiently advanced civilization, a spinning black hole could be an almost inexhaustible power source. Even a modest-sized black hole could, in principle, power a civilization for millions of years just from its rotational energy. And when that's exhausted, there might be other tricks, harvesting the energy from matter falling in, or even capturing Hawking radiation, though that would require truly astronomical timescales for any reasonably sized black hole. This is deeply speculative, of course. We don't know if civilizations advanced enough to do this will ever exist, or if they'd even want to live near black holes, but the fact that the physics allows for it is intriguing. Black holes go from being cosmic dead ends to potential engines, and from destroyers to possible sustainers of life and complexity. It's a reminder that extreme doesn't necessarily mean useless. Sometimes the most extreme environments contain the most concentrated resources, and in the deep future of the universe, when stars have exhausted their fuel and the cosmos grows cold, black holes might be among the last sources of available energy, the final fires around which any remaining complexity gathers. That's thousands of trillions of years away, if it happens at all. But it's comforting in a way to know that even in the darkness there might be light, or at least energy to sustain thought, and maybe something like life. There's a term that comes up often when people talk about black holes, and it sounds almost whimsical: spaghettification. But it describes a process that's both fascinating and, admittedly, a bit grim. It refers to what happens to objects that fall into a black hole, particularly a smaller one where the gravitational gradient is steep. Imagine you're falling feet first toward a black hole. Your feet are slightly closer to the black hole than your head, which means they experience slightly stronger gravity. The difference is small at first, barely noticeable. But as you get closer, that difference grows. Your feet are pulled harder than your head, and it's not just up and down. The gravity also squeezes you from the sides, because gravitational field lines converge toward the center of mass, so you're simultaneously being stretched vertically and compressed horizontally. For a small black hole, this tidal effect becomes extreme quite far from the event horizon. Long before you crossed it, the difference in gravitational pull between your feet and your head would become enormous. You'd be stretched thinner and thinner, pulled into a long strand like spaghetti, hence the name. Eventually you'd be pulled apart at the molecular level, then the atomic level, reduced to a thin stream of particles spiraling into the black hole. For a supermassive black hole, though, the experience would be different, because the event horizon is so much farther from the singularity. The tidal forces at the horizon itself are much gentler. You could cross the horizon of a supermassive black hole more or less intact. The spaghettification would come later, as you fell toward the singularity at the center. But you'd have time, perhaps minutes or even hours depending on the size of the black hole, between crossing the horizon and being torn apart. There's something almost poetic about the term spaghettification, a whimsical word for such an extreme fate. But it captures an important truth. Black holes don't respect the integrity of objects. They pull apart whatever falls into them, reducing complexity back to its components. And they do it not through some exotic force, but simply through gravity. The same force that keeps our feet on the ground, taken to its logical extreme. Here's a thought experiment that sounds like pure science fiction, but is actually allowed by the mathematics of general relativity. Near a black hole, there exists something called a photon sphere, a region where gravity is so strong that light itself can orbit the black hole, not fall in, not escape, but circle endlessly in a closed loop. For a non-rotating black hole, the photon sphere sits at exactly 1.5 times the Schwarzschild radius, the radius of the event horizon. Light travelling at just the right altitude and angle can loop around the black hole indefinitely, though this orbit is unstable. The slightest perturbation would send the light either spiralling inward toward the event horizon or escaping outward into space. But in principle, in that perfect moment, light can be trapped in orbit. Now imagine you could position yourself at exactly the photon sphere, which you couldn't actually do because the orbit is unstable and you'd either fall in or drift away. But set that aside for a moment. If you could hover there and look around, you'd see something extraordinary. Light from the back of your head could travel all the way around the black hole and reach your eye from the front. You could, theoretically, see the back of your own head. Not in a mirror, but directly, with light that had circumnavigated the black hole. And it gets stranger. Light could orbit the black hole multiple times before reaching you, so you might see multiple images of yourself, each one representing light that had gone around one more time. The black hole becomes a cosmic lens, bending light paths in ways that create these ghost images, these echoes of things that exist in the same place, but appear to be in many places at once. We've never seen this directly, of course. Photon spheres are far too small and far too close to black holes for us to resolve them with current technology. But we can observe the effects. Some of the light we detect from matter near black holes has likely orbited multiple times before escaping, carrying with it distorted, time-delayed information about what's happening near the event horizon. The universe has mirrors built into its structure, places where light can loop back on itself, creating reflections without surfaces. It's another reminder that in extreme gravitational fields, even something as simple and straightforward as light travelling in a straight line becomes complex and beautiful. There's a common misconception about black holes that's worth addressing, because it affects how people imagine them. The misconception is that black holes suck everything around them, that they're cosmic vacuum cleaners pulling in anything nearby. But this isn't quite right. Black holes follow the same gravitational laws as everything else in the universe. They pull on surrounding objects with a force that depends on their mass and distance, exactly like any other massive object would. If you could somehow replace the Sun with a black hole of exactly the same mass, 4 times 10 to the 30th kilograms, the orbit of Earth wouldn't change at all. We'd keep circling at the same distance, taking the same 365 days to complete one orbit. The gravitational pull at Earth's distance would be identical. Of course, we'd freeze to death in the darkness because the black hole wouldn't emit any light, but from a purely gravitational perspective, nothing would change. The Earth wouldn't spiral inward or get sucked in. What makes black holes special isn't that they have stronger gravity than other objects of the same mass. It's that they pack that mass into such a small space that you can get incredibly close to it. With the Sun, you can't get closer than the Sun's surface, about 700,000 kilometers from its center, without running into the actual matter of the Sun. But with a black hole, you can get much, much closer before you encounter anything. And gravity gets stronger with proximity. So if you fell toward a black hole, you could reach regions where gravity becomes far stronger than anything you'd experience falling toward a star of the same mass. The event horizon of a solar mass black hole would be only about 3 kilometers across. You could get within a few kilometers of all that mass, and at that distance, the gravitational pull would indeed be enormous. But from far away, it's just another mass. This is an important distinction. Black holes are extreme, but they're not magical. They don't violate conservation laws or pull harder than they should. They're just very, very compact, and that compactness allows gravity to show its full strength in a way that extended objects like stars don't permit. Sometimes the most important thing about an object isn't what it is, but how tightly it's packed. When matter falls toward a black hole, it doesn't just plunge straight in. Usually it has some angular momentum, some sideways motion, which means it spirals inward, forming what astronomers call an accretion disk. And these accretion disks are among the most energetic environments in the entire universe. As matter in the disk spirals closer to the black hole, it moves faster, following Kepler's laws of orbital motion. But here's the crucial part. Adjacent regions of the disk are moving at different speeds, and that creates friction. The inner parts are racing around the black hole many times per second, while the outer parts are moving more sedately. The shearing between these regions generates heat, enormous amounts of it. The matter in the inner disk can reach temperatures of millions or even billions of degrees. At those temperatures, matter doesn't behave like anything we're familiar with. It becomes a plasma, a soup of stripped electrons and atomic nuclei, glowing intensely across the electromagnetic spectrum. The accretion disk radiates huge amounts of energy, often more energy than entire galaxies of stars. This is the paradox of black holes. Despite being dark themselves, they can create some of the brightest phenomena in the universe simply by destroying matter in their vicinity. We don't see the black hole itself. What we see is its meal, the matter spiraling toward its doom, heated to incandescence by friction and gravitational compression. The black hole is defined by what it takes away, and revealed by what it does to its surroundings before consuming them. It's like trying to see a waterfall by watching the mist and hearing the roar. You can't see the water falling, but you can infer everything about it from its effects. Some of the most luminous objects we've ever detected, quasars, which we'll talk about more later, are powered by this process. Matter falling onto supermassive black holes at the centers of distant galaxies creates light so bright it can be seen across billions of light years. The energy doesn't come from the black hole itself, but from gravitational potential energy. The energy stored in matter by virtue of its position in the gravitational field. As matter falls, that potential energy is converted to kinetic energy, and then to heat through friction. It's one of the most efficient energy conversion processes in nature. Nuclear fusion, the process that powers stars, converts less than 1% of mass into energy. Matter falling into a black hole, depending on how fast the black hole is spinning, can convert 10% or more of its mass into radiated energy before crossing the horizon. In the economics of cosmic energy, black holes are ruthlessly efficient. Some black holes don't just create bright accretion disks, they launch jets. These are narrow beams of particles and energy that shoot out from the regions near the black hole's poles, perpendicular to the accretion disk. And when I say shoot out, I mean at velocities approaching the speed of light. These jets can extend for thousands of light years, sometimes even millions of light years, travelling across intergalactic space like cosmic searchlights. The mechanism that creates these jets is still being studied, but we think it involves the intense magnetic fields generated in the accretion disk. As matter spirals inward, it carries magnetic field lines with it, twisting and amplifying them. Near the black hole's poles, where the magnetic fields are strongest and most organised, they can accelerate particles to enormous energies and launch them outward in collimated beams. The spinning black hole itself might contribute energy through the Blandford-Znajek process we mentioned earlier, extracting rotational energy and channeling it into the jets. These jets are so powerful they can affect entire galaxies. They plough into the surrounding gas, creating enormous bubbles and cavities. They can heat intergalactic gas, preventing it from cooling and forming new stars. In a sense, the black hole at the centre of a galaxy can regulate the galaxy's growth, turning off star formation in its host by blasting away the raw material stars need to form. It's a form of feedback, a conversation between the black hole and its galaxy. The galaxy feeds the black hole, and the black hole, through its jets, tells the galaxy to slow down. What's remarkable is the scale. A black hole might have an event horizon only light hours across, smaller than our solar system. But its influence through these jets can extend across millions of light years, affecting volumes of space that dwarf the galaxy itself. It's a disproportion that's hard to wrap your mind around. An object smaller than the distance between the Sun and the outer planets, shaping structures larger than the distance between galaxies. But that's what concentrated energy can do. A small source, releasing enough power, can reshape its environment across vast distances. The universe operates on these hierarchies, these cascades of influence where tiny seeds can grow into enormous structures. Let's bring this closer to home. At the centre of our own Milky Way galaxy, about 26,000 light-years from Earth, sits a supermassive black hole called Sagittarius A star, often written as SGRA star and pronounced Sagittarius A star. It contains about 4 million times the mass of our Sun, compressed into a region smaller than Mercury's orbit. And despite its enormous mass, despite being right at the heart of our galaxy, it's remarkably quiet. By quiet, I mean it's not actively consuming large amounts of matter right now. The accretion rate onto SGRA star is very low. The black hole is essentially starving. Occasionally it flares up when a stray gas cloud or an unlucky star gets too close, but most of the time it's dormant. This is both fortunate and slightly disappointing for astronomers. Fortunate because a vigorously feeding supermassive black hole at the centre of our galaxy might make life on Earth difficult, flooding the inner galaxy with radiation. Disappointing because a quiet black hole is harder to study than an active one. Still, we've learned an enormous amount about SGRA star by watching stars orbit around it. There are dozens of stars close enough to the galactic centre that their orbits are measurably affected by the black hole's gravity. One star, called S2, orbits the black hole with a period of about 16 years. At its closest approach, it comes within about 17 light hours of the event horizon, travelling at nearly 3% of the speed of light. By tracking these stars over decades, astronomers have been able to precisely measure the mass of the black hole and confirm that it's indeed a compact object, not some other configuration of matter. It's humbling in a way. We live in a galaxy with a monster at its centre, a dark heart weighing millions of suns, and yet, from where we sit, far out on a spiral arm, it's almost invisible, detectable only through careful observation over many years. It shapes the galaxy's structure, influencing how stars move in the inner regions, but it doesn't dominate our local neighbourhood. We orbit the galactic centre every 230 million years or so, and the black hole is just one component of the total mass distribution affecting that orbit. We're safe, distant, watching from afar as stars dance around the darkness. There's a peculiar relationship between supermassive black holes and the galaxies that host them, a connection that astronomers discovered somewhat by accident and are still working to fully understand. It turns out that the mass of a galaxy's central supermassive black hole correlates remarkably well with certain properties of the galaxy itself, specifically with the mass of the galaxy's central bulge and with the velocity dispersion of stars in that region. The correlation is surprisingly tight. Galaxies with more massive bulges tend to have more massive black holes, and the ratio between them is roughly consistent across many different galaxies. This is strange when you think about it, because the black hole itself is tiny compared to the galaxy. The event horizon of even a billion solar mass black hole is only about the size of our solar system, while the galaxy's bulge contains hundreds of billions of stars spread across tens of thousands of light years. The black hole makes up only about 0.1 to 0.5% of the bulge's mass, and yet somehow these two components, vastly different in size and scale, know about each other. This suggests a kind of cosmic partnership, a coevolution where the galaxy and its central black hole grow together, influencing each other's development. Perhaps gas falling into the centre of a forming galaxy feeds both the black hole and the surrounding star formation. Perhaps the black hole's jets and winds, which we discussed earlier, regulate how much the galaxy can grow, creating a feedback mechanism that establishes the observed relationship. Or perhaps the connection goes even deeper, rooted in the initial conditions that formed both structures. We don't have the full story yet. What we do know is that galaxies and their black holes aren't independent entities but seem to be intimately linked, two parts of a single system that evolved together over billions of years. It's a reminder that the universe operates on multiple scales simultaneously, with processes at the very largest and the very smallest scales somehow coordinating to create the structures we observe. The heart of a galaxy, though tiny and dark, is somehow in conversation with the vast stellar halo around it, and they've reached an agreement about their relative sizes. For most of history, black holes were purely theoretical objects, mathematical solutions to equations that might or might not correspond to anything real. But in April 2019, that changed in a dramatic way. The Event Horizon Telescope collaboration released the first ever image of a black hole's event horizon, or more precisely, the shadow of that horizon against the glowing accretion disk surrounding it. The black hole they image sits at the centre of a galaxy called Messier 87, or M87 for short, about 55 million light-years away. The black hole itself is a giant, containing about 6.5 billion times the mass of our Sun, and yet, despite its enormous mass, despite being one of the most massive black holes we know of, it appears incredibly small in the sky. If you were to look at it with the naked eye, which you couldn't, it's far too faint and distant. It would subtend an angle about as large as an orange sitting on the surface of the moon would appear from Earth. To capture an image at that resolution required something extraordinary. The Event Horizon Telescope isn't a single telescope, but a network of 8 radio telescopes scattered across the planet. From Hawaii to Chile to the South Pole, they all observed M87 simultaneously, and their data were combined using a technique called Very Long Baseline Interferometry. Essentially, the telescopes work together as if they were a single planet-sized dish. The effective resolution was high enough to see something the size of a city on the moon, or in this case the shadow of a black hole's event horizon 55 million light-years away. What they saw was a ring of light. The photons from the accretion disk that managed to escape, orbiting just outside the event horizon, surrounding a dark circle. That darkness is the shadow of the black hole, the region where light either falls into the event horizon or orbits so close that it doesn't reach us. The image matched quite beautifully what decades of theoretical work had predicted. The size was right, the shape was right, even the brightness distribution around the ring was consistent with models. It was a moment of confirmation when mathematics and observation aligned perfectly. We finally saw one after decades of indirect evidence and theoretical predictions. The universe had a black hole, and we took its picture. Let's pause for a moment to appreciate just how massive the M87 black hole really is. At 6.5 billion solar masses, it's enormous even by supermassive black hole standards. To give that some context, if you added up the mass of every planet in our solar system, every asteroid, every comet, every speck of dust, and multiplied it by millions, you still wouldn't approach the mass of this single black hole. And yet, compressed into that mass is not just matter, but also space and time themselves, warped beyond recognition. The event horizon of M87's black hole is vast. It's about 120 astronomical units across, 120 times the distance from the Earth to the Sun. That's larger than the orbit of Pluto, larger than the entire outer solar system. You could fit many solar systems inside the event horizon of this black hole and still have room left over. And all of that space, that enormous volume, is cut off from the rest of the universe by the event horizon, a boundary as absolute as anything in physics. But here's the truly mind-bending part. Despite its enormous size, despite being one of the largest black holes we know of, it appears tiny in the sky because it's so incredibly far away. Those 55 million light-years of distance shrink the apparent size down to something that required the entire planet working together to resolve. It's a humbling reminder of the scales involved in astronomy. The universe contains objects of almost incomprehensible size, and yet the distances between them are so vast that even these giants appear as points or tiny disks. There's something almost meditative about contemplating these scales. We live on a planet that seems large to us, in a solar system that seems vast, in a galaxy that contains hundreds of billions of stars, and yet our entire galaxy would be just another speck orbiting somewhere in the halo of a galaxy like M87 if we were transported there. And at the centre of that galaxy sits this dark colossus, invisible except for the light of its last meal, bending space-time in ways that took the collective effort of hundreds of scientists and 8 observatories to capture. The universe is large, and it contains within it objects that challenge our ability to even think about them properly. But we try anyway, and sometimes we succeed. In September 2015, 2 detectors in the United States, part of an experiment called LIGO, the Laser Interferometer Gravitational Wave Observatory, detected a signal that lasted less than a second. It was a chirp, really. A rising tone that increased in both frequency and amplitude before abruptly cutting off. That chirp was the gravitational wave signature of 2 black holes, each about 30 times the mass of the Sun, merging together 1.3 billion light-years away. Let me pause to let that sink in. 2 black holes collided, releasing more energy in a fraction of a second than all the stars in the observable universe were emitting in that same instant. That energy didn't come out as light or heat or particles, but as gravitational waves, ripples in the fabric of space-time itself. Those ripples travelled outward in all directions at the speed of light, spreading across the universe, and 1.3 billion years later, after crossing an expanse of space so vast it's hard to conceptualize, those ripples passed through Earth. When they did, they stretched and squeezed space by an infinitesimal amount. The detectors, which use lasers bouncing between mirrors separated by 4 kilometers, are sensitive enough to detect changes in distance smaller than 1/10,000th the width of a proton, and they caught it. They heard the sound of space-time itself vibrating, the cosmic equivalent of a bell being rung. Since that first detection, LIGO and its European counterpart Virgo have detected dozens more gravitational wave events. Most are black hole mergers, though some are neutron-star mergers or black hole-neutron-star mergers. Each one tells us something: how massive the objects were, how they were spinning, even something about the properties of space-time in those extreme conditions. We've opened a new window on the universe, for all of human history. We observe the cosmos through light, electromagnetic radiation in its various forms. Now we can observe it through gravity as well. We can feel the universe shake, and what we're hearing suggests that black hole mergers are far more common than we once thought. The universe is alive with these events, a constant background symphony of collisions and coalescences, space-time constantly being reshaped by these violent dances. Some of the black hole mergers detected by LIGO have surprised astronomers because they created black holes that, according to our previous understanding, shouldn't exist. There's a gap in the expected mass distribution of black holes, a range of masses where we didn't think black holes should form through stellar collapse. This mass gap exists roughly between about 50 and 120 solar masses, +T, and it's related to something called pair instability supernovae. Here's the issue: when a very massive star explodes, the physics in its core can create conditions where particle-antiparticle pairs form out of the available energy. This removes pressure support from the core, causing a runaway collapse and an explosion so violent it completely destroys the star, leaving no remnant at all, no neutron star, no black hole, just scattered debris. Stars in a certain mass range should undergo this process, which means they shouldn't leave behind black holes in that mass range, and yet LIGO has detected mergers that produced black holes well into the mass gap, some approaching or even exceeding 100 solar masses. This suggests one of several possibilities. Either our models of pair instability supernovae are incomplete, or these black holes didn't form from single stellar collapse but through mergers of smaller black holes, or there are formation pathways we haven't considered. Perhaps they formed through direct collapse in dense stellar environments, or perhaps they're the product of multiple generations of mergers, black holes that have grown through successive collisions. These intermediate mass black holes occupy a fascinating middle ground in the black hole hierarchy. They're too massive to be simple stellar remnants, but too small to be the supermassive giants at galactic centers, and they might be important pieces of the puzzle of how supermassive black holes form. Perhaps they're the seeds, intermediate mass objects that merged and grew in the early universe to create the first supermassive black holes. Or perhaps they're something else entirely. They're a distinct population with its own formation history. The fact that they exist at all, in a regime where theory suggested they shouldn't, is a reminder that the universe still holds surprises. Our models are good, but they're not complete. There are gaps in our understanding, and sometimes those gaps are filled with exactly the things we thought couldn't be there. Let's talk about quasars, because they represent one of the most spectacular manifestations of black hole activity in the universe. The name is a contraction of quasi-stellar radio source, which reflects the confusion astronomers felt when they first discovered these objects in the 1960s. Through telescopes, quasars looked like stars, single points of light, but their spectra were strange, showing emission lines that didn't match any known element until astronomers realized the lines were extremely red-shifted, indicating that these objects were billions of light-years away. But if they were that distant and yet still visible, they had to be extraordinarily luminous. We're talking about objects that can outshine entire galaxies, hundreds of billions of stars, by factors of 10 or even 100, and they're not large, extended structures. Most of that light comes from a region smaller than our solar system. How do you pack that much energy into such a small space? The answer, we now know, is supermassive black holes actively feeding on enormous amounts of matter. A quasar is essentially a supermassive black hole with a particularly robust accretion disk. It is consuming matter at a tremendous rate and converting that mass into radiated energy with ruthless efficiency. The light comes not from the black hole itself, but from the superheated material in the accretion disk just outside the event horizon, heated to millions of degrees by friction and gravitational compression. What makes quasars particularly interesting is that they're most common in the distant universe, which means they were most common in the early universe, because looking farther away means looking back in time. The peak era of quasar activity seems to have been about 10 billion years ago, when the universe was only a quarter of its current age. Back then, galaxies were still actively forming, rich with gas and prone to collisions that funneled material toward their central black holes. As the universe aged and galaxies settled down, quasar activity declined. The black holes are still there. Most large galaxies have them, but they're mostly quiet now, sleeping giants starved of the abundant gas they once consumed. Our own Escray star might have been a quasar once, billions of years ago, shining across the cosmos. Now it's dormant, a relic of more violent times. One of the most puzzling aspects of quasars is how early they appear in cosmic history. We've detected quasars that existed when the universe was less than 1 billion years old, which is remarkable because quasars require supermassive black holes to power them, and we already discussed how difficult it is to grow supermassive black holes that quickly. Yet there they are in our observations, billion solar mass black holes shining brightly when the universe was in its infancy. This early existence deepens the mystery of black hole formation. If you start with a stellar mass black hole, say 100 solar masses, formed from the first generation of stars and let it grow by accreting matter at the theoretical maximum rate, it still can't reach 1 billion solar masses in less than 1 billion years. The numbers just don't work out. You need either a bigger seed, those direct collapse black holes we mentioned, or some way to feed black holes faster than the Eddington limit suggests, or perhaps both. Recent theoretical work suggests that in the dense gas-rich environments of the early universe, conditions might have allowed for periods of super-Eddington accretion, where black holes consumed matter faster than the standard models permit. Or perhaps these early quasars were powered by black holes that formed through direct collapse of massive primordial gas clouds, starting already at thousands or even hundreds of thousands of solar masses. Or maybe the first black holes grew primarily through mergers, coming together in the crowded centres of the first galaxies. What we're seeing in these early quasars is evidence of processes that happened so long ago that we're looking at light that left those objects when the universe was fundamentally different. The cosmic microwave background, the afterglow of the Big Bang, was still visible in the sky from those quasars' perspective, a warm glow filling the universe. The first stars were just forming, and yet already somehow the universe had assembled billion solar mass black holes and set them feeding voraciously. Why, it's a testament to how quickly structure can form under the right conditions, how rapidly the seeds of today's galaxies were planted in the cosmic garden. And it's a reminder that the early universe, though simpler in some ways, was capable of dramatic and rapid evolution. In May 2022, the Event Horizon Telescope collaboration released their second black hole image, and this one hit closer to home, literally. After imaging the distant M87 black hole, they turned their attention to Sagittarius A star, the supermassive black hole at the centre of our own Milky Way galaxy. And while Seer A star is much closer, about 26,000 light-years compared to M87's 55 million, it actually proved harder to image. The difficulty comes from several factors. First, SGR A star is much smaller. At 4 million solar masses compared to M87's 6.5 billion, its event horizon is correspondingly smaller. Light takes about 20 seconds to circle SGR A star's event horizon, compared to roughly a day for M87. This means the material in the accretion disk orbits much faster, changing on timescales of minutes rather than days. During the hours-long observation needed to create an image, the environment around SGR A star changes significantly, like trying to photograph a moving target. Second, we have to look through the disk of our own galaxy to see SGR A star. There's a lot of material between us and the galactic centre, gas, dust, stars, and all of it scatters and distorts the radio waves the Event Horizon Telescope observes. It's like trying to see through a thick forest, or looking at something on the far side of a campfire through the shimmering heat. The view is obscured, blurred, complicated. Despite these challenges, the team succeeded. They developed new imaging algorithms that could account for the rapid variability, essentially averaging over many different configurations of the accretion disk to extract the underlying structure. And what they revealed was beautiful. A ring of light surrounding a dark shadow, similar to M87 but unmistakably our own galaxy's black hole. The size of the shadow matched predictions. The brightness distribution was consistent with theory. It was another confirmation, another instance where decades of theoretical work aligned with observation. There's something profound about imaging the black hole at the heart of our own galaxy. It's our black hole in a sense, the one we orbit around, along with all the other stars in our galactic neighbourhood. and now we've seen it, or at least its shadow. We've mapped the boundary between what can escape and what cannot right at the centre of our cosmic home. Not all black holes stay where they formed. Some become wanderers, drifting through intergalactic space after being ejected from their home galaxies. This can happen through a process called gravitational recoil, or sometimes just called a kick. When two black holes merge, they don't just gently combine. The merger is asymmetric, releasing gravitational waves preferentially in certain directions. And since gravitational waves carry momentum, the newly formed black hole experiences a recoil, like the kick of a rifle when it fires a bullet. Usually this kick is modest, maybe a few hundred kilometers per second. That's fast by everyday standards, but it's not enough to escape a massive galaxy's gravitational pull. The black hole settles back into the galactic center, maybe with a slightly different trajectory than before. But if the merger happens in just the right way, particularly if the two merging black holes have spins that are oriented in specific directions, the kick can be much stronger. Some theoretical calculations suggest kicks of thousands of kilometers per second are possible, enough to eject even a supermassive black hole from its host galaxy entirely. These rogue, or wandering, black holes would travel through intergalactic space, carrying with them whatever small amount of material they managed to hold onto from their original galaxy. They'd be nearly impossible to detect directly, since they're not actively feeding and therefore not producing much radiation. Nay, but we might see them occasionally when they pass through gas clouds or disturb the motion of nearby stars. There's some observational evidence for these wanderers, though confirming they're actually ejected black holes rather than some other phenomenon is challenging. Imagine it, a supermassive black hole, once the gravitational anchor of an entire galaxy, now adrift in the void between galaxies. It would travel for billions of years through nearly empty space, a cosmic nomad. Perhaps eventually it would encounter another galaxy and be captured, settling into a new home. Or perhaps it would wander forever, a relic of a long-ago merger, condemned to solitude in the darkest reaches of space. It's a lonely thought, but also oddly compelling. Even the universe's most massive, most gravitationally dominant objects can be cast out. You're set adrift by the violence of their own interactions. Here's something that came as a surprise when astronomers first measured it. Some black holes appear to be spinning backwards relative to their accretion disks. In other words, the black hole rotates in one direction, but the material orbiting it in the accretion disk is moving in the opposite direction. This is called retrograde accretion, and it tells us something about the black hole's history. If a black hole grows smoothly, accreting material consistently from the same direction over time, its spin and its accretion disk should align. The black hole would spin in the same direction as the material orbiting it, like a record player where the record and the turntable rotate together. But if the black hole has a chaotic history, if it grew through mergers with other black holes approaching from random directions, or if it accreted material from different sources at different times, the spin direction might not match the current accretion flow. Retrograde accretion has some interesting consequences. For one, it affects how efficiently the black hole can accrete matter. The innermost stable orbit, the closest distance at which material can orbit before spiraling into the event horizon, is farther out for retrograde accretion than for aligned accretion. This means there's a larger gap between the accretion disk and the event horizon, which can affect things like jet formation and energy extraction. But what makes this really fascinating is what it tells us about the black hole's biography. A retrograde spin is like a scar, evidence of past trauma. It suggests that this black hole didn't have a simple, quiet life of steady growth. It experienced disruptions, mergers, chaotic accretion events that changed its spin direction. By measuring spin directions, astronomers are essentially reading black holes' histories, reconstructing their life stories from the clues encoded in their rotation. Some black holes have smooth histories, others have violent ones, and you can tell the difference by watching how the black hole and its dinner plate spin relative to each other. Black holes aren't just passive inhabitants of galaxies, they actively shape the galaxies they live in. This happens through a process called AGN feedback, where AGN stands for active galactic nucleus, which is just astronomer speak for a supermassive black hole that's actively feeding. Do you know, when a black hole consumes matter, it releases enormous amounts of energy through radiation and jets, and that energy doesn't just disappear into space. It interacts with the surrounding gas in the galaxy, heating it, pushing it around, sometimes even expelling it entirely. Here's why that matters. Stars form from cold, dense gas. If you want to make new stars, you need gas clouds that can collapse under their own gravity, fragmenting into stellar nurseries. But if a black hole heats the surrounding gas or blows it out of the galaxy entirely, that gas can't collapse and form stars. The black hole, in effect, regulates star formation. It acts as a cosmic thermostat, preventing its host galaxy from converting all its gas into stars too quickly. This feedback mechanism might explain some puzzling observations about galaxies. For instance, the most massive galaxies tend to have very little ongoing star formation, despite having plenty of gas. They're red and dead, as astronomers sometimes say, full of old red stars but not making new ones. The supermassive black holes in these galaxies might be responsible, their past activity having heated the gas enough to prevent it from cooling and collapsing. It's a delicate balance, really. The galaxy feeds the black hole, and the black hole, through its activity, regulates how the galaxy grows. Too much feeding, and the black hole might shut down star formation entirely. Too little, and the galaxy might form stars too rapidly and exhaust its gas supply. Somehow, over cosmic time, a balance is struck. That same balance that creates the correlation between black hole mass and galaxy properties we discussed earlier. The universe has a way of finding equilibrium, even in systems as violent and extreme as galaxies with active black holes. It's not harmony exactly. It's more like a conversation conducted in jets and radiation, with the structure of entire galaxies hanging in the balance. When LIGO and Virgo started detecting gravitational waves from black hole mergers, one of the surprises was just how often these events happen. Before gravitational wave astronomy, our estimates of merger rates were based on indirect evidence. How many binary black hole systems we thought existed, how long they should take to spiral together, that sort of thing. And those estimates suggested that mergers should be relatively rare events, maybe a few per year in the observable universe. But the actual detection rate turned out to be much higher. In their latest observing run, LIGO and Virgo were detecting black hole mergers roughly once every few days. Extrapolating to the entire observable universe, this suggests tens of thousands or even hundreds of thousands of these mergers happening every year. The universe is absolutely alive with the sound of black holes colliding, a constant background chorus of space-time ringing. This high merger rate tells us something important. Either there are more black hole binaries than we thought, or they merge faster than our models predicted, or both. It might mean that black holes form more readily in binary systems, perhaps in dense stellar clusters, where stars are packed closely enough that captures and interactions are common. Or it might mean that the mechanisms that bring black holes together, things like dynamical friction and gravitational wave emission, are more efficient than we realized. Each detection adds to our statistical understanding. We can look at the distribution of masses, the distribution of spins, how often mergers produce black holes in that forbidden mass gap we talked about. We're building up a census of the black hole population, learning what masses are common, what merger configurations happen most frequently. It's like doing astronomy through a completely new sense. We're not seeing the universe, we're feeling it shake. And what we're feeling suggests that the cosmos is far more dynamic, far more violent, far more alive with mergers and collisions than we previously imagined. The universe isn't static, it's constantly rearranging itself, and black holes are major players in that ongoing reorganization. Sometimes a black hole doesn't exist in isolation or merge with another black hole. Sometimes it orbits a normal star, slowly consuming its companion in what astronomers call an X-ray binary system. These systems are fascinating because they give us one of the best ways to study black holes that aren't supermassive, that aren't at the centers of galaxies, but are just out there in the stellar population, living ordinary lives as cosmic vampires. In a typical X-ray binary, you have a black hole orbiting a companion star, maybe a massive blue star or a red giant. The two orbit their common center of mass, held together by gravity. Yeah, but the black hole's gravity is so strong that it pulls material off the surface of the companion star. This material doesn't fall directly into the black hole. Remember, it has angular momentum, so it forms an accretion disk, and as we've discussed, accretion disks get hot. For stellar mass black holes, the inner parts of the disk can reach tens of millions of degrees, hot enough to radiate primarily in X-rays. That's how we detect these systems, through their X-ray emission. The companion star is visible in optical light, just a normal star as far as telescopes can see. But pointed at the same location with an X-ray telescope, you see intense X-ray emission from the accretion disk around the invisible black hole. By watching how the companion star moves, how it wobbles in its orbit, how its spectral lines shift due to Doppler effects, astronomers can measure the mass of the unseen companion. If that mass exceeds about 3 solar masses, which is the theoretical maximum for a neutron star, you know you're looking at a black hole. These systems are sometimes called stellar death spirals, and there's a certain dark poetry to that. The companion star is doomed. Slowly, over millions of years, the black hole will consume it, pulling away its outer layers, feeding on its mass. Eventually there might not be enough of the companion left to sustain nuclear fusion, and it will fade away, leaving just the black hole behind, now slightly more massive than before, enriched by its meal. It's a slow, inexorable process, a gravitational relationship that can only end one way, and yet for now, the system is stable. The two objects locked in their dance, one shining and one dark, one dying and one feeding. Sometimes the accretion disk around a black hole doesn't quite line up with the black hole's spin axis, and when that happens, something strange and beautiful occurs. The disk wobbles. This phenomenon is called lens-Thirring precession, and it's another consequence of frame dragging, that effect where a spinning black hole drags space-time around with it. Imagine the accretion disk as a spinning coin, and imagine that the black hole's spin axis isn't perfectly aligned with the coin's spin. The frame dragging effect is stronger closer to the black hole, so the inner parts of the disk feel a stronger torque, trying to align them with the black hole's spin. The outer parts, being farther away, feel a weaker effect. This creates a torque across the disk, causing it to precess, to wobble like a spinning top that's been nudged off vertical. We've observed evidence of this precession in some X-ray binaries. The X-ray emission shows periodic variations consistent with our view of the inner disk changing as it precesses around the black hole's spin axis. It's like watching a wobbling coin from the side. Sometimes you see it edge on, sometimes more face on, and the amount of light that reaches you changes accordingly. What makes this particularly interesting is that the precession rate depends on the black hole's spin. A rapidly spinning black hole causes faster precession than a slowly spinning one. So by measuring how quickly the disk wobbles, astronomers can infer how fast the black hole is spinning. Which in turn tells them something about the black hole's history. A rapidly spinning black hole might have grown through steady aligned accretion. A slowly spinning one might have experienced chaotic accretion or multiple mergers that cancelled out its spin. Once again, we're reading the black hole's biography, this time through the wobble of its dinner plate. There's something hypnotic about imagining these precessing disks, these cosmic gyroscopes misaligned with their anchors, slowly wobbling through cycles that might take weeks or months to complete. The universe contains these intricate mechanical dances governed by gravity and relativity, playing out in environments so extreme we can barely conceive of them. And we can detect them, measure them, learn from them, which is its own kind of wonder. Here's an idea that pushes the boundaries of our current understanding. Some physicists have suggested that supermassive black holes might have formed not from ordinary matter, but from concentrations of dark matter in the early universe. Dark matter, that mysterious substance that makes up about 85% of the matter in the universe, but interacts only through gravity, tends to collect in halos around galaxies. In the early universe, these dark matter halos might have been incredibly dense in their central regions. The hypothesis goes like this. If a dark matter halo was dense enough, it might have collapsed gravitationally into a black hole directly, without ever forming stars or going through any of the usual astrophysical processes. The dark matter would just keep falling inward under its own gravity until it reached densities high enough to form an event horizon. And because dark matter doesn't radiate, it doesn't emit light or heat or interact electromagnetically at all, the collapse wouldn't be slowed by radiation pressure the way ordinary matter collapse would be. This could potentially solve the puzzle of how supermassive black holes form so quickly in the early universe. Instead of starting from stellar mass seeds and growing through accretion and mergers, these black holes would be born already massive, products of dark matter dynamics rather than stellar evolution. Once they existed, they could then accrete ordinary matter and grow even larger, eventually becoming the supermassive monsters we observe. It's a speculative idea, and we don't have direct evidence for it yet. Dark matter remains mysterious. We know it exists because of its gravitational effects, but we don't know what it's made of, or precisely how it behaves beyond its gravitational interactions. But if dark matter can form black holes, it would be yet another pathway to creating these objects, another recipe in the universe's cookbook, and it would mean that black holes aren't just the remnants of stars or the products of ordinary matter dynamics. They could also be direct sculptures of the dark matter that silently shapes the cosmos. The visible and the invisible meeting at the most extreme endpoint of gravitational collapse. Now we come to one of the deepest puzzles in modern physics, something called the black hole information paradox. And it's a paradox because it sits at the intersection of two fundamental theories, general relativity and quantum mechanics, which give contradictory answers to a simple question. What happens to information that falls into a black hole? Quantum mechanics, at its core, insists that information is never truly destroyed. If you know the quantum state of a system at one time, you should be able to calculate its state at any future time, and in principle, work backward to reconstruct its past. Information is conserved. It might become scrambled, spread out, effectively impossible to access in practice, but it's still there, encoded somehow in the universe. This is called unitarity, and it's one of the foundational principles of quantum theory. But general relativity tells a different story. According to classical general relativity, anything that falls past the event horizon is gone. It falls toward the singularity and is, for all intents and purposes, erased from the universe. An outside observer can never retrieve that information, and if the black hole eventually evaporates through Hawking radiation, which we discussed earlier, the situation seems even worse. Hawking radiation in its original formulation is purely thermal. It's just random heat, carrying no information about what fell into the black hole. So when the black hole finally evaporates completely, all that information appears to be permanently lost. This creates a contradiction. Quantum mechanics says information can't be destroyed. General relativity says it falls into the black hole and disappears when the black hole evaporates. Both can't be true, so which is it? Or is there some deeper synthesis that resolves the paradox? Physicists have been grappling with this for decades. Some proposals suggest that information is somehow encoded on the event horizon itself, preserved in subtle correlations in the Hawking radiation that we haven't yet understood how to detect. Others suggest that the interior of the black hole remains connected to the outside in ways we haven't fully grasped, perhaps through quantum entanglement. Still others propose more radical ideas, that black holes don't have singularities at their centers, or that the event horizon isn't what we think it is. We don't have the answer yet. The information paradox remains one of the most important unsolved problems in theoretical physics, a signpost pointing toward the theory that will eventually unite quantum mechanics and gravity. And there's something almost comforting about that uncertainty. Here we are, with all our instruments and mathematics and careful observations, and we still don't know what happens to information in a black hole. The universe keeps some secrets, and this is one of them. Let's think for a moment about what it means that we can never observe the interior of a black hole beyond the event horizon. This isn't a limitation of our technology or our cleverness. It's written into the fundamental structure of space-time. No signal, no information, no light can escape from beyond the horizon to reach us, which means the interior of a black hole is, in principle, forever hidden from scientific inquiry, at least from the outside. This creates a strange situation. We can write down equations describing what happens inside the horizon. We can predict that someone falling in would experience tidal forces that eventually tear them apart. We can calculate what the space-time geometry looks like all the way down to the singularity, but we can never check those predictions against observation. We can never test them. The interior of the event horizon is a realm of pure theory, where the mathematics takes us but observation cannot follow. Some philosophers of science have wondered whether this means statements about the interior of black holes are even meaningful. If a prediction can never be tested, is it really physics, or is it just mathematics? But most physicists are comfortable with the situation. The theory that predicts the exterior of black holes, general relativity, works magnificently in every regime where we can test it. It seems reasonable to trust it in the one place where we can't. And besides, the equations don't stop at the horizon. They continue smoothly inward, describing a continuous space-time geometry. It would be strange if nature suddenly switched to a different set of rules right at the boundary we can't see past. Still, there's something profound about this limitation. The universe contains regions that are, in principle, forever beyond our direct knowledge. We can observe their outsides, their effects, the shadows they cast. But their interiors remain mysteries, accessible only through mathematical extrapolation and theoretical reasoning. Perhaps that's fitting. Perhaps it's even necessary. A universe where everything could be observed and measured might be one where there's no room left for mystery, and no edge where our knowledge gives way to wonder. Black holes give us that edge. They're the cosmic equivalent of "here be dragons" on ancient maps, boundaries beyond which we cannot go, can never go, but can still contemplate. Here's a more optimistic thought about black holes. They might someday be useful. This sounds strange. Useful how? They're millions of light years away, and even if we could reach them, they'd destroy everything that gets too close. But in the truly long term, in the far future, when the universe has aged and changed beyond recognition, black holes might be the last energy sources available. We've already talked about the Penrose process, the mechanism by which you could theoretically extract energy from a rotating black hole's ergosphere. And we've mentioned that this might not be just theoretical, that natural astrophysical processes might already be using this mechanism to power jets from black holes. But imagine taking this further. Imagine a civilization advanced enough to build structures around a black hole, deliberately dropping material into the ergosphere and harvesting the energy released. The concept is sometimes called a black hole engine, or, in its most extreme form, a black hole power plant. You'd position yourself in orbit around a spinning black hole, and carefully drop objects into the ergosphere at angles designed to extract the maximum rotational energy. The physics allows for this. You could, in principle, extract a significant fraction of the black hole's spin energy, potentially enormous amounts of power, far more than you could get from nuclear fusion or any conventional energy source. And here's what makes this particularly interesting for the far future. Black holes last. Stars burn out. Galaxies disperse. Planets cool. But black holes, especially large ones, can persist for unimaginable timescales. In the deep future, trillions upon trillions of years from now, when the last star has faded and the universe is dark and cold, black holes might be the only game in town. If anything resembling life or consciousness persists that far into the future, it might cluster around black holes, drawing on their residual energy to sustain thought and complexity. This is purely speculative, of course. We have no idea if civilizations that advance will ever exist, or if the universe will even support complexity on those timescales. But the fact that the physics permits it is wonderful in itself. The darkest, most destructive objects in the current universe might become the lighthouses, or at least the power sources, of the distant future. Here's where things get really strange. The mathematics of rotating black holes, specifically the Kerr solution to Einstein's equations, contains some deeply weird features. For a rotating black hole, the singularity isn't a point, it's a ring. And if you approach this ring singularity along certain paths, the equations suggest you might be able to pass through it and emerge into somewhere else. Perhaps another region of space-time, perhaps another universe, perhaps even another time. These solutions allow for what are called closed time-like curves, paths through space-time that loop back on themselves, which would mean you could, in principle, travel into your own past. Now, before we get too excited, there are several enormous caveats here. First, these are purely mathematical solutions. We don't know if the interior of real black holes actually looks like this, or if quantum effects or other physics we don't understand would change the picture entirely. Second, even if the mathematics is right, there are questions about whether these paths are traversable in practice. The tidal forces might be unsurvivable, or the singularity might not actually be a clean ring but something more complicated. And third, there's the question of whether closed time-like curves lead to logical paradoxes. If you could travel into your own past, you could potentially create situations where you prevent yourself from travelling in the first place. The classic grandfather paradox of time travel stories. Some physicists argue that this means closed time-like curves probably can't exist in reality, that nature finds some way to forbid them, perhaps through quantum effects that we don't yet understand. But the fact that they show up in the mathematics at all is fascinating. General relativity, this theory we trust because it predicts so many things correctly, contains these wild possibilities. It's like discovering a secret room in a house you thought you knew perfectly. Whether that room is physically real or just a mathematical curiosity remains an open question. But rotating black holes, at least according to the equations, might contain within them pathways to other places and times. The universe, it seems, is stranger than we've imagined, and our best theories suggest it might be stranger still. There's a theorem in black hole physics with a wonderfully evocative name, the no-hair theorem, and it states something remarkable. A black hole, once it settles down after formation, can be completely described by just 3 numbers: its mass, its electric charge, and its angular momentum, how fast it's spinning. That's it. Everything else, every detail about what fell in to make the black hole, all the complexity of the matter that collapsed, is erased, or at least hidden behind the event horizon. Imagine 2 black holes, each with the same mass, charge, and spin. One formed from the collapse of a massive star. The other formed from the accretion of 1,000,000 smaller objects. According to the no-hair theorem, those 2 black holes are indistinguishable. They have the same event horizon, the same space-time geometry around them, the same gravitational and electromagnetic effects. An outside observer could never tell them apart. This is sometimes phrased as black holes have no hair, meaning they have no distinguishing features beyond those 3 numbers, no bumps, no irregularities, no memory of their formation. In a sense, black holes are the simplest macroscopic objects in the universe. All the complexity that went into making them gets compressed into 3 quantities. This simplicity is both beautiful and troubling. And beautiful because it suggests an underlying elegance. The universe takes arbitrarily complex configurations of matter and reduces them to a handful of parameters. Troubling because it seems to violate information conservation, which brings us back to the information paradox. If all the details of what fell in are truly erased, then information has been destroyed, which quantum mechanics says shouldn't happen. Recent work suggests that the no-hair theorem might not be the complete story. Perhaps black holes have subtle quantum hair, information encoded in ways too subtle for classical general relativity to capture, but recoverable in principle through quantum effects. Or perhaps the interior of the black hole, though inaccessible to us, still contains all that information. and it gets released somehow when the black hole finally evaporates. The jury is still out, but for now the no-hair theorem stands as one of the most striking features of black holes. They're amnesiacs, objects that have forgotten their own history, or at least hidden it so completely that it might as well not exist. Let's entertain one of the most mind-bending ideas in cosmology, that our entire universe might exist inside a black hole in a higher dimensional space. This isn't mainstream physics, and it's not something most cosmologists actively work on, but it's mathematically plausible and worth contemplating, especially on a night like this when we're letting our minds drift through cosmic possibilities. The idea starts with an observation about the mathematics. When you write down the equations for our expanding universe, the Big Bang cosmology, and compare them to the equations for the interior of a black hole, they have certain similarities. Both describe spaces that are expanding. Both have a boundary separating inside from outside. Both have regions where the usual coordinates break down. Some physicists have wondered, could these similarities be more than coincidence? One version of this idea suggests that when a black hole forms in some higher dimensional universe, the collapse creates not just a singularity, but an entire lower dimensional universe inside. From the outside, in that higher dimensional space, it looks like a black hole. But from the inside, it looks like a Big Bang, an expanding universe with matter and energy and eventually stars and galaxies. Our Big Bang, in this view, wasn't the beginning of everything. It was the interior of a black hole forming in some parent universe we can never observe. There's no way to test this, at least not obviously. If we're inside a black hole, the event horizon is in our past. It's the Big Bang itself, in a sense. We can't see outside it, can't communicate with the parent universe, can't gather evidence about what's out there. The idea might be forever untestable, which makes it more philosophy than physics by some definitions. But it's a haunting thought, isn't it? That all of this, galaxies, stars, planets, us, might be the interior structure of a black hole in some larger cosmos. That our universe's expansion is just the geometry of the black hole's interior, playing out in dimensions we interpret as space and time. That somewhere outside, in a space we can't conceive of, our entire reality is just a dark point, a gravitational singularity that has consumed some mass and now contains within it a universe. Perhaps every black hole we observe is the same. Perhaps each one contains its own universe, its own Big Bang, its own eventual structure and complexity. Perhaps black holes aren't endpoints but beginnings, seeds of new realities. Or perhaps it's all just a mathematical curiosity, a similarity in equations that doesn't correspond to physical reality. We may never know, but the possibility alone is worth contemplating. Here's another deep puzzle that emerged from trying to reconcile quantum mechanics with black holes, the firewall paradox. This one is more recent than the information paradox, emerging from work in the 2000s, and it presents a stark choice between two things we thought we understood about black holes. On one hand, we have the equivalence principle, Einstein's insight that someone in free fall doesn't feel any forces, that the laws of physics should look the same in free fall everywhere, even at a black hole's event horizon. This suggests that crossing the event horizon should be smooth, uneventful, nothing special happening at that boundary. You just keep falling. On the other hand, we have arguments from quantum mechanics suggesting that for information to be preserved when a black hole evaporates, to avoid the information paradox, The Hawking radiation coming off the black hole needs to be entangled with the black hole's interior in a specific way. But here's the problem: you can't have both. If the Hawking radiation is entangled with the interior in the way needed to preserve information, then the event horizon can't be smooth and uneventful. Instead, according to these calculations, it would be a firewall, a region of extremely high energy that would incinerate anything trying to cross it. An infalling observer wouldn't smoothly enter the black hole. They'd be destroyed at the horizon by a wall of high-energy particles. This contradicts the equivalence principle, which has been confirmed by countless experiments and observations, and is one of the foundations of general relativity. So we have a choice. Either the equivalence principle fails at black hole horizons, or information isn't preserved in black hole evaporation, or our understanding of quantum entanglement is incomplete, or something else entirely is going on that we haven't figured out yet. The firewall paradox remains unsolved. Different physicists favour different resolutions, and there's no consensus. Some argue that the equivalence principle must be sacrificed, that black hole horizons really are violent places. Others insist that there must be some subtle mistake in the firewall argument, that a more complete understanding of quantum gravity will dissolve the paradox. Still others propose that the very notion of a sharp event horizon breaks down when you account for quantum effects properly. What I find striking about this is that it emerged not from observation, but from thought experiments. From pushing our theories into regimes where they start to contradict each other. We're uncovering puzzles through pure reasoning, and finding places where our understanding is incomplete just by thinking carefully about implications. And the fact that the puzzle exists suggests we're close to something important, some boundary in our knowledge where new physics must emerge. The universe is giving us hints, through paradoxes and contradictions, about where to look next. Let's talk about white holes, because they're the theoretical mirror image of black holes, and they're deeply strange. If a black hole is a region where nothing can escape, a white hole would be a region where nothing can enter. It would be like a black hole running backward in time. Instead of matter falling in and disappearing, matter would pour out and nothing could fall back. White holes appear in the mathematics of general relativity, and they're allowed by the equations in the same way that black holes are. If you take the Schwarzschild solution, the simplest black hole, and extend it fully, you get not just a black hole region but also a white hole region, connected through the interior in a configuration called a Schwarzschild wormhole or Einstein-Rosen bridge. In this mathematical structure, the black hole and white hole are two mouths of a tunnel through space-time. But here's the thing, we've never observed a white hole. Not one. And there are good reasons to think they might not exist in reality, even though the math allows them. For one thing, white holes would violate the second law of thermodynamics in obvious ways. They'd be sources of low-entropy matter pouring into the universe, creating order from nothing. For another, they'd be unstable. While even a tiny amount of matter approaching a white hole horizon would accumulate there, and calculations suggest this would cause the white hole to collapse or transform into something else. Some physicists have speculated that white holes might have existed in the early universe, perhaps as the other side of primordial black holes, but that they decayed quickly and are gone now. Others suggest that what we perceive as the Big Bang might be related to white hole physics, a one-time event where matter poured into the universe through something like a white hole horizon. These are highly speculative ideas, far from the mainstream of astrophysics. But the fact that white holes exist mathematically as valid solutions to Einstein's equations is still fascinating. They're like the universe's unrealized possibilities, roads not taken. Like black holes are real, confirmed, observed. White holes are their theoretical shadows, allowed by the same physics but apparently not chosen by nature, or at least not chosen in the current epoch of the universe. Perhaps in different conditions at different times they could exist. Perhaps they did once. Or perhaps they're purely mathematical, beautiful structures that inhabit equation space, but not the physical cosmos. Either way, they remind us that the map, the mathematics, often contains more than the territory, and not everything that can be written down in equations necessarily exists out there among the stars. If Hawking radiation is real, and most physicists believe it is, even though we've never observed it, then black holes eventually evaporate. And that means the universe has a timeline, a cosmic story that includes the eventual disappearance of even these most permanent-seeming objects. Let's trace that story into the far future, shall we? For large black holes, the evaporation timescale is almost unimaginably long. A solar mass black hole would take about 10 to the 67 years to evaporate completely. That's a 1 followed by 67 zeros, a number so large it defies intuition. The current age of the universe is only about 10 to the 10th years, 13.8 billion years. So we're talking timescales longer than the current age of the universe by a factor of more than 10 to the 50. It's not just millions or billions of times longer. It's longer by an amount that itself requires scientific notation to express. Supermassive black holes last even longer. A billion solar mass black hole might take 10 to the 100 years or more to evaporate. These are timescales that dwarf the current age of the universe to the point of irrelevance. But they're finite. Given enough time, even these giants will disappear. And here's the strange part. As a black hole evaporates, it gets smaller, and as it gets smaller, it evaporates faster. The process accelerates. So the final moments of a black hole's life would be dramatic. A period of rapid mass loss, the black hole heating up as it shrinks, eventually culminating in a final burst of energy as the last bits of mass convert to radiation. A black hole dies not with a whimper, but with a bang, though that bang won't happen for any existing black hole for an almost incomprehensibly long time. In the truly distant future, perhaps 10 to the 100 years from now, the universe might be a cold, dark place. All stars will have burned out. All planets will have cooled. Galaxies will have dispersed as their stars drift away, and the last black holes will be evaporating, slowly giving back to the universe the mass they accumulated over cosmic ages, and then, eventually, even they'll be gone. The last black hole will evaporate in that final flash, and the universe will be left with nothing but a thin soup of radiation, growing ever more diffuse as space continues to expand. It's a melancholy thought in some ways, that even these most enduring objects eventually fade. But there's also something almost peaceful about it. Nothing lasts forever, not even the things that seem most permanent. The universe runs down, entropy increases, and eventually even the black holes return to light. We've come a long way through these facts, from the basic definition of what a black hole is to the deepest paradoxes and the farthest future. And here, at the end, it's worth stepping back and appreciating what black holes really represent in our understanding of the universe. They sit at the intersection of our two greatest theories, general relativity and quantum mechanics, and they're the places where those theories break down, where they give contradictory answers, where new physics must emerge, General relativity describes gravity, space-time, the large-scale structure of the cosmos. It works magnificently, predicting everything from planetary orbits to gravitational waves with stunning precision. Quantum mechanics describes the world of the very small, atoms and particles and fields. It also works magnificently, underlying all of modern chemistry and electronics and giving predictions confirmed to absurd levels of precision. But these two theories don't fit together. They use different mathematical languages, different conceptual frameworks. And when you try to apply both at once, in the extreme conditions at a black hole's singularity, or in the subtle quantum effects at the event horizon, you run into problems, contradictions, paradoxes. This tells us something profound. Our understanding is incomplete. We have two excellent theories, but we need something deeper, a theory of quantum gravity that encompasses both. That theory, whatever it turns out to be, will change how we think about black holes. It might tell us what really happens at the singularity, whether information is truly preserved, whether firewalls exist, and whether the universe in a black hole idea has any merit. It might reveal entirely new aspects of these objects that we haven't even thought to ask about yet. Black holes are more than just astrophysical objects. They're laboratories for testing the limits of physics, natural experiments that push our theories into regimes we could never access artificially. They're puzzles that nature has left for us, challenges that say, your theories are good, but they're not complete. Keep looking, keep questioning. There's something deeper to discover. And in that sense, black holes are invitations to wonder, to question, to push beyond what we know into what we don't yet understand. They're dark, yes, but they illuminate the boundaries of our knowledge, and that's a different kind of light entirely, perhaps the most important kind. The light that shows us not what we can see, but where to look next. And so, we've journeyed through 50 facts about black holes, from their formation to their eventual evaporation, from the mathematics that predicts them to the observations that confirm them, from what we know to what we're still puzzling over. We've seen how they shape galaxies, how they merge and create gravitational waves, how they challenge our understanding of information and time and the very nature of reality. Black holes remind us that the universe is stranger than we're built to imagine. Our intuitions evolved in a world of moderate gravity and human-scale speeds, a world where time flows steadily and space is flat and objects are either here or there but not somehow in between. Black holes operate in a different regime, where space-time itself is twisted into impossible shapes, where the future becomes a direction you can't avoid falling toward, where the boundary between inside and outside is more profound than any wall. And yet, for all their strangeness, they're real. They exist, scattered throughout the cosmos, sitting at the hearts of galaxies, wandering through intergalactic space, forming in the depths of massive stars, merging in spectacular collisions. They're part of the furniture of the universe, extreme but not rare, challenging but not impossible to understand. We've imaged them, heard them merge, mapped their effects on surrounding stars and gas. Perhaps what's most remarkable is that we can understand them at all, that sitting on this small planet using mathematics and observation and careful reasoning, we can figure out what happens when matter collapses so completely that it creates a rupture in space-time. That's worth marveling at, that capacity we have to reach beyond our immediate experience and grasp truths about the universe that we could never witness directly. So as you drift off tonight, you might think of those black holes out there, those dark hearts beating at the centers of galaxies, those wanderers drifting through the void, those binaries slowly spiraling together toward eventual merger. They're part of the cosmos you inhabit, part of the same universe that contains your bed and your pillow and the light falling gently through your window. The universe is one thing, containing multitudes, from the gentlest falling leaf to the most extreme gravitational maelstrom. And in understanding even a fraction of it, in grasping even imperfectly what a black hole is and how it works and what it tells us about reality, you've connected with something larger than yourself. You've touched the edge of the cosmic mystery, and that's a good thought to carry into sleep. The universe is vast, strange, wonderful, and you're part of it, contemplating it, trying to understand it. That's enough for one night. Rest well.